Okay, students, this time I shoot the video in different mode. Let us check this mode. And I am coming with another question, 2014 question. Look at this question. Which of the following molecule is chiral? You have given A, B, C, D option and you have to find out the answer. This question comes from your topic optical activity due to special type of molecules which does not contain normal chiral carbon atoms. This is called cumulative double bond. This is biphenyl. First, let us discuss cumene. Then there is spirans, then biphenyl. How they could be optically active and how will you find out this? That's our target. Cumenes or not cumenes, allenes. Allenes means, what are allenes? Not cumene, allene. Allene is the molecule, organic molecule having cumulative double bonds. Cumulative double bonds. You know what is cumulative double bond? Cumulative double bonds, nothing but one double bond, another double bond, like this. Okay? This is cumulative double. This is the a double bond, single bond, double bond. This is what is we called double bond, single bond, double bond. This is called conjugation. But this system is called cumulative double bond or allenes. Therefore, allenes are the molecule having adjacent double bonds, double bond upon double bonds. Now, we have two types of allenes. One is odd number double bond. Second is even number double bond. Let me check how the shooting is going on. Okay, fine. Odd number double bond and even number double bond. Odd number double bond. This is odd number. 1. Let me draw. C double bond C, double bond C, double bond C. 3. Even means C double bond C, double bond C. 2. 2 or 4 like that. 2, 4. That is 2, 4, 6, 8 like that. Here are 3, 1, 3. Okay, 1 double bond. That is also in this category. 5, 7, 9 like that. This molecule, odd double bond, cannot show optical isomerism. It can show optical isomerism. Therefore, here 1, 2, 3. Whatever the condition, it cannot show optical isomerism. One double. It shows geometrical isomerism. It shows geometrical isomerism, not optical isomerism. One double bond, that is cis and trans isomer, 1, 3, 5, 7, shows geometrical isomerism. Remember my students, one double bond alene shows geometrical isomerism. You know, this is trans. This is why, you know, when there is when there is odd number of double bonds, this is a condition. Suppose you have one double bond, second double bond, second will be here, okay, and the third will be here. Therefore, the groups are this H and Cl in this notebook, upon this notebook, this H and Cl in this diary. Both are this diary on the plane of the board. This is perpendicular to plane of the board, but this book is plane of the board. Therefore, if there is odd number of double bonds, Cl and H, this Cl and H are on the plane of the board, like this, plane of the board. They have a planar symmetry. Okay? They are like eclipsed configuration. They are like eclipsed configuration. They have a planarity. They are just like Cl and this Cl and H, this Cl here, H here, and on the board. That Cl and H on the board. Therefore, if there is 1, 3, 5, 7, 9 double bonds, that molecules have the planarity. They shows geometrical isomerism, not optical isomerism. Okay, only 2, 4, 6, 8 double bond molecule shows optical isomerism. So only if the conditions, the groups attached here red, here blue, that is the groups attached in A and B, suppose here C and D, this A and B, this should not be equal. A should not be equal to B, C should not be equal to D. The groups attached in allenes will be optically active. Allenes will be optically active. Allenes will be optically active only if they have even number of double bond, and the group attached here should be different. A, B. You can have A here, you can have a B here. No problem. No problem. Only the condition, it should not be equal. It should not. This is optically active. This is optically active. Now I give another example. C double bond C, A, B, B, D. A not equal to B, B not equal. These groups are different. Therefore, they are optically active. Or it can be C and D, no problem. Okay? Okay? This is not optically active, which A, B, D, D. This is not optically active because these two groups are same. The allenes will be optically active if two conditions should be satisfied: even double bond and different groups on carbon. Even double bonds plus different groups on carbon. Different groups on carbon. Okay, even double bond, but here groups are same. Same, not optically active. This is already not optically active because odd number of double bond. Now come here, even. This is not equal. This is also. This is answer. Now what about D, option D? That is called biphenyl. Here the answer is C. But what about the biphenyls? Biphenyl. Biphenyl means two phenyl ring. Biphenyl means two phenyl ring. Yes. Here should be two different groups. You just imagine this is double bond number 1, it is double bond number 2. A, B, C, D. A should not be equal to B, C should not be equal to D. That's all, nothing more. A should not be equal to B, C should not be equal to. Okay, but there is a condition. If hydrogen, deuterium, fluorine comes together in any benzene, that is optically inactive. That is optically inactive. Suppose here you have an hydrogen, here are fluorine, here hydrogen, here chlorine. Okay, you satisfied two double bond, not equal, but hydrogen and fluorine should not come on same carbon atom, same benzene ring. You know why? These are the smaller group. Because of these two smaller group, you know, these benzene rings are like this. One benzene ring is this, second benzene ring is this. That is why it has an optical activity. And here a single bond, because we know that single bond always rotates. Here, but rotation is restricted because of these two groups. If these two groups are smaller, like hydrogen and hydrogen, deuterium, fluorine, they have a tendency to rotate like this and planarity. Therefore, smaller groups should not be on the benzene ring, even if it is if they are different. Smaller group should not be on same benzene ring. What are the three smaller group? Hydrogen, deuterium, and fluorine. That should not be on same benzene ring. That's only the condition. I will tell you in the suppose you have here Cl, optically active. Two are different. Now both are Cl. It is optically inactive because these two groups are same. If these two groups are same, they have a plane of symmetry. You know, suppose these two groups are same. Here chlorine are same. You can cut them into equal planes. Optical activity because of non-planarity. I mean, there should not be any symmetry elements. That is the basic reason. Therefore, this is optically inactive. But if it is H, optically active. But if it is F, optically inactive. Because fluorine is smaller groups. Because of the smaller group, this benzene get rotated and both benzene will be on same plane. Fine. Now another case is spiran. What is spiran? Spiran means molecules like, I will give you one beautiful example. Molecule like this. This is called a spiran. You have nothing worry about it. This is double bond number, double bond 2. You have two groups HCl. Optically active. Now you have another molecule HCl. Optically inactive because these are same. Now you have another problem. HCl. Is it optically active? No, it's optically inactive. Why? Because 1, 2, 3. Odd number rings cannot be optically active. Double number, even number rings will be optically active if groups attached are different. Now, students, suppose you will have a question like this. C double bond C. Suppose a molecule like this, double bond HCl, ClH. Another molecule ClH, ClH or HC. Which is optically active? Here 1, 2, 1, 2, 3. This is optically inactive because odd number of rings and double bond together. Here even, now groups are different, optically active. Okay, very simple, very simple. Now R and S nomenclature of this molecule will be discussed in another occasion. Okay, I think this topic is clear for you. Any doubts? Welcome.